Planetary landers represent a critical component in the exploration of other worlds within our solar system, embodying a complex amalgamation of science and technology designed to perform the daunting task of delivering payloads from space to the surface of another planet. The development and successful operation of these landers require a multifaceted understanding of aerospace engineering, robotics, material science, and environmental adaptation strategies to tackle the unique challenges presented by different planetary environments. The primary function of a planetary lander is to transport scientific instruments and sometimes rovers to a planet's surface, ensuring a safe touchdown in environments that can vary from the thin, carbon dioxide-rich atmosphere of Mars to the harsh, cryogenic surface of Europa. Achieving this feat involves several key technological components and systems, each designed to handle specific phases of descent and operation upon landing. Entry, descent, and landing, EDL, systems. One of the most critical aspects of lander technology is the EDL system, which must be meticulously designed to handle high-speed entries into planetary atmospheres and ensure a soft landing. For instance, Mars landers utilize a combination of heat shields, parachutes, retro-rockets, and sometimes airbags to slow down and cushion the landing. The heat shield must withstand and dissipate the intense heat generated by atmospheric entry. Following this, parachutes are deployed to reduce speed further. In the final descent stage, retro-rockets or thrusters are often used to slow the lander down to a safe landing speed. For bodies without an atmosphere, like the Moon, landers rely solely on rocket thrusters to decelerate and guide the lander to the surface. Navigation and guidance systems. Advanced navigation systems are crucial for ensuring landers reach their intended landing site. These systems typically combine data from onboard star trackers, accelerometers, and gyroscopes with preloaded celestial maps to accurately guide the descent trajectory. In recent missions, technology such as terrain relative navigation, TRN, has been employed to enable landers to autonomously avoid hazards in the landing zone by comparing real-time surface imagery with onboard maps. Robotic systems and payloads. Once on the surface, the scientific objectives of the mission begin. Planetary landers carry a variety of scientific instruments designed to study the planet's geology, atmosphere, and potential for life. These instruments can include spectrometers, weather monitoring devices, cameras, and drilling systems, all built to operate in alien environments. Robotic arms and sampling tools are often controlled remotely from Earth, allowing scientists to interact with the planetary environment indirectly. Power systems. Powering these instruments and the lander itself is another significant challenge, particularly in environments far from the Sun where solar power is less feasible. Many landers use radioisotope thermoelectric generators, RTGs, which convert heat released by the decay of a radioactive material into electricity. This type of power supply is long-lasting and reliable, essential for missions extending over years or in shadowed regions of planets. Communication systems. Maintaining communication with Earth is crucial for the success of any lander mission. High-gain antennas are typically used to transmit large volumes of data over the vast distances between planets, while low-gain antennas provide a constant but lower bandwidth link for command and control messages. The data transmitted often includes not only scientific data but also health and status information about the lander's systems. Materials and structures. The materials used to construct landers must be capable of withstanding extreme temperatures, corrosive atmospheres, and radiation. Engineers use a combination of composites, metals, and insulating materials tailored to the specific conditions expected on the target planet. Testing and simulation. Before a lander ever reaches its target, it undergoes rigorous testing on Earth. This testing includes thermal vacuum chambers to simulate the temperature and vacuum of space, vibration testing to simulate launch conditions, and full-scale landing rehearsals using models or virtual simulation technologies. In conclusion, the science and technology behind planetary landers integrate various fields of study and innovation, culminating in machines capable of exploring other worlds. As our knowledge and technology advance, future landers will be increasingly sophisticated, perhaps one day paving the way for human landings on planets like Mars. The continued development of planetary landers not only pushes the boundaries of what is technologically possible but also expands our understanding of the universe.